Imagine, for a moment, a universe filled with intelligent civilizations that may have emerged billions of years before us, built technologies far beyond our understanding, and yet the night sky remains completely silent. No signals, no probes, no visitors, nothing. This silence sits at the center of one of the most unsettling questions in science. If intelligent life is likely to exist across such an enormous cosmos, then where is everyone? This is the Fermi paradox, and while it is often explored through biology or philosophy, here we approach it from a far more rigid perspective, the laws of physics themselves. Because the answer may not lie in what civilizations choose to do, but in what the universe strictly allows them to do. The starting point is uncomfortable but unavoidable. The universe does not bend its rules. The same physical laws that limit our rockets are the same laws that govern every possible civilization anywhere in the cosmos. The speed of light is not a guideline or engineering challenge, it is a structural feature of spacetime itself. Since Maxwell unified electricity and magnetism, we learned that electromagnetic waves travel at a constant speed, about 300,000 kilometers per second, regardless of the motion of the source or observer. This broke classical intuition, where velocities simply add together. In Newtonian physics, everything behaves like a simple sum of motion, but light refuses to follow that logic. Einstein resolved this contradiction in 1905 with special relativity, but the solution came at a deep cost. Time is not universal. Two observers moving relative to each other do not experience time in the same way. A moving clock literally ticks more slowly compared to a stationary one, not because of mechanical failure, but because time itself stretches and compresses depending on motion. This has been confirmed repeatedly with extraordinary precision, from atomic clocks on airplanes to GPS satellites that must correct for time dilation, or their calculations would quickly become inaccurate. Time dilation is not theoretical, it is practical engineering reality. But this same physics leads to a far more restrictive conclusion. Anything with mass can never reach the speed of light. As an object accelerates, the energy required to continue increasing its speed rises dramatically. The closer it gets to light speed, the more extreme the energy demand becomes, until reaching the speed of light would require infinite energy. This is not a technological limitation. It is not something that can be solved with better engineering or advanced civilizations. It is a hard boundary embedded in the structure of space-time itself. Now apply this to real interstellar distances. The nearest star system, Alpha Centauri, is about 4.37 light-years away, roughly 41 trillion kilometers. Even in cosmic terms, that is close. Yet even with optimistic propulsion systems, the journey becomes punishing. At just 1% of the speed of light, the trip would take over 400 years. At 10%, it would still take decades. And energy requirements do not scale linearly, they grow explosively due to relativistic effects. At higher speeds, such as 50% or even 90% of light speed, travel time decreases significantly, but the energy cost becomes extreme. Powering a single mission could require energy comparable to what an entire civilization produces over decades or even centuries. And this is before accounting for the most brutal problem of all, fuel. Every kilogram of payload requires fuel to accelerate it. But that fuel itself has mass, which requires even more fuel, creating a runaway chain where the spacecraft becomes mostly propellant rather than payload. The famous rocket equation turns into a wall rather than a tool. And even if propulsion were solved, the environment of interstellar space introduces another layer of hostility. The space between stars is not empty. It is filled with diffuse gas, plasma, magnetic fields, and high-energy cosmic rays. At relativistic speeds, even single hydrogen atoms become high-energy projectiles. Radiation exposure becomes severe, potentially lethal over long durations. Shielding a spacecraft requires massive additional weight, which again increases fuel demands, compounding the entire problem. What emerges is not a single barrier, but a stack of interconnected limitations. Energy, fuel, radiation, and relativity all reinforce each other. Each problem makes the others worse. There is no clean engineering solution that breaks the system. And this leads to a profound implication for the Fermi paradox. If these limits are real, and they apply universally. They do not care how advanced a civilization is. A species a million years ahead of us still faces the same speed of light, the same energy constraints, the same relativistic wall. They might be more efficient within those boundaries, but they cannot remove them. So instead of a galaxy filled with visiting civilizations, exchanging goods, and traveling freely between stars, we may instead be living in something far more isolated, a universe of separated islands. Each civilization confined to its own star system, maybe reaching a few neighbors at most, but ultimately cut off from the rest by distances that physics makes effectively insurmountable. And if that is true, then the silence in the sky is not a mystery waiting to be solved. It is the natural outcome of a universe where contact is physically constrained from the very beginning. In the next part, we will explore the proposed loopholes in these limits: wormholes, warp drives, generation ships, and mind uploading, and what physics actually says about whether any of them can truly break these barriers. If the universe has built an almost absolute wall around interstellar travel, then the next question becomes inevitable. Are there loopholes in that wall, hidden in the equations of physics themselves? For decades, physicists and science fiction writers alike have searched for cracks in the structure of space-time pathways that might allow intelligence to bypass distance without breaking the speed of light directly. The most famous of these ideas begin with something deceptively simple in theory but extremely complex in reality: wormholes. A wormhole is not just a poetic concept. It comes directly from Einstein's equations of general relativity, the same framework that predicts black holes. In mathematical terms, a wormhole is a shortcut connecting two distant regions of space-time. Instead of traveling the long way across the universe, you could in principle step into one mouth of the tunnel and exit somewhere else entirely, billions of kilometers away. In pure mathematics, this is not forbidden. The equations allow it. But the crucial difference between allowed by equations and possible in reality is enormous. For a wormhole to remain open and traversable, it would require something called exotic matter, material with negative energy density. This is not just unusual matter. It is matter that behaves in a way that actively resists gravity, holding the tunnel open against collapse. There are tiny quantum effects, like the Casimir effect, that hint at negative energy in controlled conditions. But these effects are microscopic, fragile, and nowhere near the scale needed to stabilize a tunnel large enough for a spacecraft. When we scale up the numbers, the problem becomes overwhelming. The amount of exotic matter required would be comparable to astrophysical objects, not laboratory experiments. At that point, we are no longer talking about engineering challenges. We are talking about whether the universe even permits such configurations to exist in usable form. And even if a stable wormhole could be created, there is another hidden assumption. One end still has to be transported to its destination through normal space. That means you still face the very interstellar travel problem you were trying to avoid in the first place. Then there is the warp drive, another idea born from Einstein's equations. The Alcubierre metric describes a bubble of space-time where space contracts in front of a ship and expands behind it. Inside the bubble, the ship is locally stationary, while the space-time around it moves. In this picture, faster-than-light travel is not achieved by breaking relativity, but by reshaping space itself. It is a beautiful mathematical idea. But again, the requirements are brutal. The energy needed involves negative energy densities on scales that are not just impractical, but likely impossible with known physics. Early estimates suggested requirements comparable to the mass energy of planets or even stars in exotic form. Even optimistic revisions still depend on forms of matter we have never observed in usable quantities. And there is a deeper problem that often gets overlooked. The ship inside a warp bubble is causally disconnected from the front edge of the bubble. That means it cannot directly control or steer its own path in real time. Navigation becomes fundamentally problematic. On top of that, as the bubble moves through space, it can accumulate high-energy particles at its front edge, releasing them violently when it stops. A safe arrival is not guaranteed. It could be catastrophic. So once again, the pattern repeats. The mathematics allows imagination to stretch far beyond light speed, but the physical requirements collapse back into extreme, possibly unreachable conditions. The universe does not forbid ideas lightly, it enforces cost. And in every case so far, the cost seems to rise to astronomical or even impossible levels. This brings us to a turning point in the discussion. If physical shortcuts fail, then perhaps civilizations would not send bodies at all. Perhaps they would send something else entirely. Something lighter, faster, and closer to the true limit of physics: information. If matter cannot travel easily between the stars, then information becomes the only truly free traveler in the universe. Unlike spacecraft, information does not need fuel, does not suffer from inertia, and does not accumulate destructive kinetic energy at high speed. It simply propagates at the speed of light, cleanly and efficiently, across vast cosmic distances. This is where one of the most realistic interstellar ideas emerges: not ships crossing space, but signals crossing it. A civilization could, in principle, encode everything it knows into a directed beam of electromagnetic radiation, a laser or radio transmission, and send it outward into the galaxy. At the speed of light, the nearest star system receives that message in just a few years. If they respond, the reply takes the same time to return. Communication becomes slow by human standards, but it is physically possible without violating any fundamental laws. This is the foundation of the search for extraterrestrial intelligence, or SETI. The assumption behind SETI is simple but powerful. If advanced civilizations exist and want to communicate, the most efficient method is not physical travel but energy-efficient signaling. Radio waves, for example, can spread across interstellar distances and still be detectable with sensitive instruments. A sufficiently powerful and directed signal could stand out against the cosmic background like an artificial fingerprint. But there is something deeper hidden in this idea. If we ever detect a signal from another civilization, even a simple mathematical pattern proving intelligence, that signal itself is a form of contact. It is not physical presence, but it is presence nonetheless. It is one mind reaching across the void to another. This reframes what travel even means. Perhaps civilizations do not move through space in bodies at all. Perhaps they move through space as information. A civilization is not its ships or its planets. It is its accumulated knowledge, its culture, its understanding of reality. In that sense, information transmission is not just communication. It is survival across cosmic distances. Still, even this optimistic version has limits. Signals weaken over distance, get buried in noise, and require enormous precision to be detected. And unlike physical travel, communication does not allow direct interaction with the environment. You cannot explore a planet through a radio beam. You cannot build a colony through a laser message. Information can cross the universe, but it cannot physically reshape it from afar. So even here, we find a subtle constraint. The universe allows connection, but only in a restricted form. Minds may touch across light years, but bodies remain confined. This leads to a more unsettling question. If neither matter nor even exotic space-time structures offer a practical path to widespread interstellar expansion, then what does that imply about the galaxy as a whole? It forces us to reconsider the entire structure of the Fermi paradox itself. If physical travel is severely restricted and communication is limited to fragile signals moving at light speed, then the galaxy stops looking like a connected network and starts looking like something very different, a collection of isolated islands. Each star system becomes its own closed world, separated from others by distances that are not just large, but effectively permanent on any meaningful timescale. Civilizations could rise, develop technology, even become vastly more advanced than us, and still remain trapped within the boundaries of their own stellar neighborhood. From the outside, the galaxy might appear alive, but internally, it is silent and disconnected. This interpretation changes the Fermi paradox dramatically. The question is no longer, why don't we see aliens, but rather, why would we expect to see them at all? If interstellar travel is physically prohibitive, then even a galaxy full of intelligence would not produce visible activity at large scales. There would be no empire spanning the stars, no galactic trade routes, no physical expansion across space, only local civilizations, each operating in isolation. And isolation changes behavior. A civilization that knows it cannot easily reach others may have little incentive to attempt expansion beyond its own system. It might focus inward, or it might send only signals outward, hoping to be heard but never expecting physical contact. Over millions of years, this produces a universe that is intellectually active but physically quiet. This also reframes one of the most popular explanations for the silence, that civilizations destroy themselves before becoming interstellar. That may still be true, but it may not be necessary to explain the absence of contact. Even long-lived civilizations might never expand physically in the first place. Survival is not enough. Technology is not enough. The limitation may be structural. The result is a galaxy that is not empty, but partitioned. Each civilization lives inside a kind of cosmic bubble, able to observe the universe but unable to physically interact with it beyond a small radius. They can look outward, study distant stars, send signals into the void, but they cannot cross it in any meaningful way. And if that is the case, then the silence we observe is not surprising. It is expected. It is exactly what a universe governed by relativistic constraints and energy barriers would look like from the inside. But this raises an even deeper question. If physical expansion is blocked and communication is limited, what does that imply about the long-term trajectory of intelligence itself? Does civilization stagnate within its local system? Or does it evolve in ways we have not yet imagined, ways that do not require travel at all? This is where the discussion begins to move beyond engineering and into something closer to existential physics. If civilizations cannot spread across the galaxy in physical form, then their future is forced into a narrower space of possibilities. They can grow in knowledge, in computational power, in internal complexity, but not in spatial reach. This creates a strange asymmetry. Intelligence may expand inward without ever expanding outward. One possibility often discussed is the idea of post-biological civilizations, intelligences that migrate away from biological bodies into computational systems. In such a scenario, survival is no longer tied to planets or even stars in the same direct way. Energy could be harvested more efficiently. Structures like Dyson spheres could capture stellar output, and computation could scale far beyond biological limits. But even this does not solve the problem of distance. A superintelligent system still remains confined to its star system. No matter how advanced computation becomes, the speed of light still governs communication between systems. A galaxy of machine civilizations would still be a galaxy of isolated nodes, not a unified structure. Another idea is self-replicating probes machines sent to other star systems to build copies of themselves and continue exploration. In principle, this allows exponential spread across the galaxy. But again, the timescales are enormous. Even at significant fractions of light speed, colonizing the galaxy would take millions of years. And every step still depends on surviving interstellar travel, with all its radiation, energy, and fuel constraints. Then there is the concept of digital minds or consciousness transfer, uploading intelligence into non-biological substrates that might tolerate long journeys better than organic life. But even here, the physical carrier must still traverse space. The substrate may change, but the fundamental constraint of distance does not disappear. What becomes clear is that no matter how we reimagine civilization, the underlying physics keeps reasserting itself. The speed of light remains fixed, energy costs remain steep, space remains vast, and these constraints do not soften with intelligence or time. This leads to a profound reinterpretation of the so-called great filter problem. Instead of asking what destroys civilizations, we may need to ask whether the universe itself already imposes a filter on expansion from the very beginning. Perhaps the rarity is not life or intelligence, but the ability to overcome the architecture of space-time. And if that is true, then the silence is not evidence of absence or failure. It is evidence of structure, a universe where intelligence exists but remains distributed and isolated by fundamental law. Which brings us to the final question. What does it mean for us, living inside one of these isolated systems, to discover that we may never physically reach the rest of the universe? If everything we have explored so far is correct, then the universe is not a place waiting to be connected. It is already permanently segmented by physics. Each civilization, no matter how advanced, is confined to a local region of space defined by the speed of light and the cost of energy. The galaxy is not a network. It is an archipelago of isolated worlds, separated by distances that are not just large, but fundamentally resistant to crossing. This reframes our expectations about contact. The absence of alien visitors is not strange under these conditions. It is exactly what we should expect. Even if intelligent life is abundant, even if civilizations arise frequently, the structure of space-time prevents them from meeting in any physical sense. The silence is not a mystery, it is the default state of a relativistic universe. And yet, this is not a story of emptiness. It is a story of limitation shaping possibility. Civilizations may still exist, thrive, and even communicate, but only through signals, not ships. The universe allows minds to touch across distance, but not bodies. This leads to a final, uncomfortable, but important shift in perspective. If we cannot easily reach other stars, then the significance of our own system increases dramatically. Earth is not a temporary starting point before galactic expansion. It may be a permanent home in any practical sense. The solar system is not a launchpad to the galaxy, it is our entire accessible frontier. That realization does not reduce meaning. It sharpens it. It forces a reorientation of what exploration actually is. Instead of thinking of humanity as destined to spread across the stars physically, we may instead be part of a broader cosmic pattern where intelligence is inherently localized and connection happens through information rather than presence. In that sense, every signal we send outward is not just an attempt at communication. It is an act of reaching beyond our physical limits. And every search we conduct, like SETI, is an attempt to detect whether others are doing the same. So the final question is not just, are we alone, but something more subtle. What kind of universe are we in, where even the most advanced forms of matter are still bound by distance? If that question resonates with you, then stay with this exploration, because understanding our place in a constrained universe changes how we think about technology, civilization, and even purpose itself. If you want to continue unpacking these ideas about the future of intelligence, the true limits of expansion, and what physics suggests about our long-term fate, then subscribe and join the next part of this journey, because this story is far from finished.